next part, as I said that already, logistic regression is nothing but the classification, because basically when you do the regression with qualitative variables, it becomes classification. So in terms of classification, when we learn, that's why the logistic regression comes first. Since we have done quite a bit, so it will take a little less time. But in general way, classification, as I said, I used like to say that regression is the most popular and useful technique you need to know. Some people claim classification is the most useful, but as I'm making the relationship, essentially, if you know the regression, you know the classification as well. But in practice also, people familiar with much more classifying this part. For example, a person arrives in the emergency room. Usually people comes in. Emergency room means definitely they don't know for what reason it is coming. And then some people working in the front desk, they have to observe the immediate some symptoms, and they have to decide which department would go, whether it's surgery or it is orthopedics, or which department it will go, because it is the patient cannot say, right? And oftentimes, given the symptoms when they see, it's not clearly determined whether it will go which department, right? It is not obvious. So you have to make a choice, and this choice are attribute to the class of one of the departments. I don't know how often people take again it's a subjective choice, but if you have a system built up using this previous data, of course your data size would be very high. Then when the new patient comes in, you try to match the symptoms with some existing things, and you will see what's the most likelihood from the past data, which department it should be, then you will send it to them. That doesn't mean that you take a always right decision, but in probabilistically you take the best decision. So that's the way it's the classification. Online banking service, this is another good example where you really have to use this type of machinery, but essentially it is regression or classification. You must have to determine whether or not transaction being performed on this site is fraudulent on the basis of user's IP address, transaction history. Because why it is? Because every day we are using our credit card, either buying a train ticket, this, that, all purposes from online, right? Like when I'm in US, actually I bought all this ticket by myself using my credit card. But definitely this credit card is making some number of checks before they permit me to buy the ticket. And what they're doing, that's the best few information usually you give, IP address, all these things. And sometimes you might see that some kind of notification, it is verified by your bank. So what does it mean? Immediately they send this IP address name to your issuing bank, and then issuing bank is looking all this history and etc. It comes back, and then it's making this check that, okay, this is the person, this is the type of history, it is approved. So it's not that your bank is approving, still where you are purchasing, they are approving the whole thing, but there are a number of checking going on, and then they are making a decision whether it will be, the online banking service will be given or not. Bigger problem, biomedical engineering, over day after day it's coming, still it is not yet commercialized, still in the lab. When the patient is coming, when you are prescribing the medicine, typically we do the medicine based on some of the symptoms, but that a couple of symptoms can match to everybody. For example, you came with a fever, say 99 degree, then whoever comes in 99 degree gets the same medicine, right? But nowadays when you are in, immediately we can take your DNA sequence, or it is already there in the record, and because of the DNA differences, possibly there could be much more appropriate match, and which could be making sense? So what does it mean? That means you are estimating mean for different person to the different one, and then you have to do the regression. But so classification, you have to do this part. But this becomes this high dimensional one, which you cannot do with the existing thing. That's some of the things what we have been talking. When all these things would be established in the machine, everybody actually trying nowadays. Everybody. That's how personalized medicine people are working, how to build up the whole thing. Okay. So that's why classification is important, but in general way, regression is important. Generally, it is the qualitative response. Predictive qualitative variable is commonly known as classification. So what is classification? As I said, that basically, if you know what is regression, then regression with qualitative variables is this, or you can think about that. Predicting qualitative means we can do the prediction in regression as well. So essentially anything related to the qualitative is the classification. These are the kind of these simple things which we will do today, but there are many more things which we cannot do everything, like you know that support vector machines, random forest, all sorts of things are there, but these are most powerful thing in terms of much more versatile and easy to understand, easy to implement. So commercially used techniques are mostly here, but the others are not really commercially used. Okay, but down the line it will be, someday it will be. This is already we talked about. Qualitative response always required, assigned. You have to assign a numerical values, and what the numerical values would be. As I said that I wanted to say, so for example, if we go to the, when it was a two possibilities, you do this 1, 0, that was, do the logistic regression, it was easy. But suppose you have this one and there are three possibilities, three medical possibly be attributed to one of the three medical conditions, means one of the three medical units they can go. How do you code it? I can code it 1, 2, 3. And then how the way we did logistic regression, once we coded 1, 0, then right hand side your features are exactly the same, right? So here also I can do 1, 2, 3, right hand side exactly the same, and now we can interpret that risk in terms of the beta coefficient, right? But 1, 2, 3 possibly when I'm in the desk, I'm using the 1, 2, 3, or I'm hospital A, I'm doing this 1, 2, 3. But hospital B might be using 3, 2, 1, right? Then mathematically you can see that for the same data set, in the left hand side it is changing 3 to 1, 2, 3 to 3 to 1, and you are running the same code, but because of the 1, 2, 3 becomes 3 to 1, your regression coefficient can be completely different. As a result, for the same patient, the risk calculation for hospital A might show completely different in hospital B, unless there is a unified way. So that's what it is required to have a clear description how the will do, or their unified system has to build up. Otherwise, you cannot do this thing. Everybody understand what is my point? Okay. So that's why you, oftentimes, in particularly statistics class, we do not pay any attention. We just say, oh, okay, you can do this part. It is not true. It is much more difficult thing, and its implication is huge. Unless we develop this system, the implication means the whole information may be different once you in one hospital to the another hospital, or one person to the another person, it completely different. So when the whole data science can build up, everything has to build up simultaneously. So I'll skip this logistic regression because we have done already, and computation wise already I said that why it is pretty well developed in all software, so you can use these things as a binomial under the generalized linear model family. By the way, it is called generalized linear model because the linear model, but there are a number of other cases also we can capture which we are not talking here. That's okay, we don't need to. Now the second category. So logistic regression we said, and everybody understood that this can be used as a classification. Another most popular one is the linear discriminant analysis. Many of you heard about, but it is also again similar thing, but work completely differently. So what does it mean? unlike the logistic regression, we model the distribution of the predictors y. So what is the x? X is the feature vector, right? And y is the qualitative quantity. In a logistic regression, what we did, qualitative is we made it numeric, and then we put a distribution on that qualitative characteristic, like binomial distribution. So in other words, we have the randomness or stochastic process defined on your response variable in the logistic regression, and feature was assumed to be fixed. There is no distribution attached, or there is no probability distribution. Like given this feature x, age, this, what should be my y? That's the way we did, right? Logistic regression works completely differently. What it assumes, there is a distribution on the feature, no distribution in the outcome variable. Outcome, like it's a kind of just a factor, class factor. There is no stochasticness. So feature means like whatever the symptom, like income, blood pressure, or whatever it is, that you have to assume some distributions. So you can understand at this right from the beginning, by assumptions, two things are completely different. And since it has this type of assumptions, oftentimes logistic regression can be more robust because there is no assumption for this x, provided your model is right. On the other hand, here it is required that x has some probability distribution needed. Then what probability distribution you can put? You have to know number of probability distributions. Generally, again, we know the normal distribution most well. We do not know really all other distributions. That's why everything could be normal. So first assumption we'll start with, we'll assume that the distribution is normal. If we do that thing, then the model itself would look very similar to regression, but as I said that it works differently, but it will look similar, okay, under the assumption of normality. But if we do not assume the normality, then it could be completely different, and we don't know, and we do not like to talk at this point if it is not assumed. So what does it mean? Then if in a practical sense, if you are working in a feature vector, if the feature vector has lots of qualitative factors, this may not be immediately useful, because you know that if it is lots of qualitative factors, this no longer may be Gaussian distribution, because you are artificially making these numbers. So immediately you get the sense that when the logistic regression could be more useful rather than the LDA. Everybody is clear? So that's why it is very important that you understand the assumptions behind. On the other hand, if these assumptions hold, then this is often more stable than the logistic distributions. Even computationally, it could be much faster, much easier than the logistic regression. Okay? So what it is? As we said, this is your feature vector. You have to assume a distribution, given that this is the symptom or this is the qualitative thing. What was in logistic regression? Logistic regression, we assume a probability model for y given that x, right? Remember that in the logistic regression that was the model. But here model is completely other way around. Probability distribution of x given that y. So it makes other type of, not only the Gaussian assumptions you need, you know that your feature vector dimension can be very high, but always your response usually work with 1 or 2 or 3 type of dimension, right? So in that way, logistic regression was better because you have to work at the most 1-dimensional probability distribution or 2-dimensional probability distribution. But here the probability distribution you have to define as many feature vectors you have, as many risk factor you have. So that's the probability distribution. Dimension will go very high immediately. Everybody is clear? Okay. Then you need the second thing. So K denotes the, suppose there is K class, okay? 1, 2, 3, 4, 5 classes, like our medical experiment 3 classes. In risk group, high risk, low risk, so K equal to 2. So given in pi K, maybe the prior probability that is coming from Kth class. So you know what's the probability that given that feature X, the person belongs to Kth class. It's a prior means it doesn't depend even on the feature. So in some way, suppose you are classifying, looking at characteristics of an image, you like to classify whether it's a male or female. Okay? Then prior probability, probably by default you can say hap, because without knowing anything you can put male or female equal to hap. But in some cases when you don't know, what you can do, look at the training data, and in training data see how many of the image match with the male, how many image match with the female. In the training set you know the answer, and from there you can calculate the empirical proportion, and that empirical proportion can give you the pi k. Okay? Alright, so we have to know these things. Then if I apply the Bayes theorem, I remember that you guys did the Bayes theorem. By the way, I had this other question, right, that you flipped the second time, and did you get the answer, anybody? Okay, you can keep right now, but I will come back. This is interesting, because there is a reason why I asked. So you say the Bayes theorem is very important. So once I have this, because in the Bayes you have a prior, this is the kind of the likelihood, and then you calculate the posterior. So coming back, this looks like the, again, logistic, that what's the probability that it is in the kth class, given that new vector, new feature, like when the new person comes in, his feature is x, then what's the probability that that person will belong to the kth class? So then use the Bayes theorem. If you have apply the Bayes theorem, then this probability would be prior probability times this likelihood part divided by sum over all these things. Okay? So again, that's what as a foundation Subro did some of this Bayes, but you can do this part. So after calculation it looked like a logistic type of thing, but nevertheless this is also a random variable. In a logistic regression this was not a random variable. So this is the thing, right? So idea would be, basically we have to calculate this thing and then try to, so but this is the Bayes. So we can actually use, which the another classifier I did not write, you can define a Bayes classifier. What would be, I can calculate, so given a new person when comes in, I can calculate what's the probability that he will be class 1, what is the probability that he is in class 2, what's the probability that he is in class 3, then I look at the highest probability and I will just assign. So that could be the Bayes classifier. Okay? But LDA goes one step further. Alright? So you got to know already logistic classifier, Bayes classifier, which I won't talk much because we don't really use. LDA would be using the Bayes classifier. So coming back, it is easy to calculate so I already said this thing. This could be challenging, definitely. But if it is normal, probably it should be okay. But if it is higher dimensional normal, it would be really challenging, because higher dimensional normal means you have not only the mean vector, you have the covariance matrix. Think about even if you have the 3 features, say age, income, and education, then 3 by 3 covariance matrix you have to estimate, which immediately have number of more parameters. That's why it is too much difficult to handle. So let's start with, suppose we have one, that's, since it is more complicated, we start with just one predictor variable, that means one feature, and assume that this is Gaussian. Okay? So that means what is this thing? I am assuming that if x is my income, the distribution of income at each class, group 1, group 2, group 3, group 4, is a normal distribution with certain mu k and sigma k square. That means mean varying, sigma varying. But at this point, the LDA defines, assume that the variability is the same. What does it mean? That means if I am trying to classify, say, low income group, middle income group, high income group, or rather than, because low, middle, high is not a very good example, male and female. Or male female transgender, if you like to do that way, then what you are saying, their mean features are different by mu k, but the variability, because if there are 2% there is a variability, the variability is within the class 1, within the class 2, within the class k, all are same. Okay? So that's simplified, by doing this simplification, actually you are reducing the number of parameters as well mathematically. If this is case, then your Bayes calculation becomes that the previous one, if I plug in this whole thing, this guy, under these Gaussian assumptions, it becomes like this. Okay. Again, nothing you need to really go through, do the details, because eventually you'll learn some formula and use some package, but you need to understand what's going on between. Now, if I take the log, then the rule is the new observation to the class K, or to the class, for which after doing little bit of algebra you can calculate, this is kind of the delta, which is the classifier, which involved x is the new feature, that means new guy comes, is the vector. This is the mean vector for the kth class, this is the variance for each of them, you calculate, and this is the prior probability. Whichever is the large, you just assign that one to the class. Okay? So that's very simple in some sense. Of course, you can see that this is not usable because these are the parameter we don't know, so we have to estimate this parameter, and then you have to plug in, so it would be estimated estimator rather than. So this is, that's why oftentimes this type of estimator we call, it's a two-stage estimator. One is first by doing this Bayes estimator you calculate this thing, then you have to estimate the parameter plugged in, so this would be double hat type of thing. Okay? Get little bit of, so this is defined kind of the LDA. Let's have some little bit of discussion. When k equals to 2, that means 2 class, and suppose they are pi 1 equal to pi 2, that means say male and female, half and half probability. The Bayes classifier assigns an observation to class 1 by doing some simplification if this guy bigger than difference of the square of the means, and class 2 otherwise. So it is kind of this is the observation for the new person, difference of the mean times 2 bigger than square of the differences of these two means. That's the thing. And when they equal, equality means this thing happens. Typically this is called the boundary line. So that means if the x value is here, you are undecided where you will put, because the rules is already defined here. If it is bigger than this, then it goes to class 1, otherwise class 2. But what if it is the equal? Then essentially we call this is a boundary. Okay? Now here is the, in picture, how does it look like? Suppose I know, so one dimensional Gaussian, so the distribution in class 1 like this, that the distribution of the, say, income of group 1 is like this. So this is the lower income group. And distribution of the higher income group is like here, where mean is definitely higher. That's why, but their variability is the same. You can see that the two curve has the variability the same, right? So naturally, now you get a new person whose income is right here. Obviously, from this where you can see that it will belong to this class. Obviously, it will belong to this class. But how about I get a person who falls in here or here or here? Then there is a, particularly this region, this the common area becomes the complicacy, and that as much commonality would be, that would create how much error we are going to make. As much likely it would be in this area, less likely that we will make a mistake. The more closer to the boundary, we will make the more mistake. The new observation comes to the boundary, which makes sense, right? If the new person comes in, if he is very close to the poor class family, immediately you said the poor, easy to identify. But there are some people where you cannot identify, that should be here. And then basically you have to calculate this probability, and which based on the probability will do these things. So this is kind of the ideal situation if it is, and you can calculate actually how much would the misclassification could be. How much would the the proportion of the group 1 can be misclassified to the group 2, this for the probability. The proportion the people who are really in group 2, they could be classified as group 1, whatever this area defined. So I can calculate the exact, if I knew this curvature, I could calculate the exact probability what's the percentage of people you will misclassify. Everybody is clear? But in reality, I don't know this thing. So I have to estimate the curve from the data. Again, you get the training data set from this group to both the group. You estimate that mean and then the common variance. And suppose these are the estimated curve. Because why it is histogram? Because you generated basically the data from this curve, generated the data from this curve, and this is the estimated curve essentially. Okay? And the dotted line is still, it's kind of the theoretical boundary, but boundary expression I showed you. Now I can estimate that boundary things as well. The estimated boundary is this solid line. Okay? Then what we did for this one, you just bring number of new data point which were not in my training set. So it's a testing set. And I tried to calculate, or I tried to classify using the classifier whether it is in this group or whether in this group. This is the portion, you can see that light gray shaded, and this is here little bit of small portion which are misclassified. That means they are actually here, but my classifier classified it here. And similarly, you can see some of the green part here. What does it mean? That the new guy which came in, they should have been classified here, but my classifier did it here. So from this plot, I can calculate what is this much of the probability and what is this much of the probability. Right? Because if I approximate in a Gaussian way, I can calculate those probabilities pretty well. And for this example, those probabilities would be so okay. I think already I said this person. If the new observation x is less than 0, there's Bayes class. Forget it. In real situation, you don't know this thing. The linear discriminant analysis method approximate this Bayes classifier by plugging in this estimator. That's already I said. So this portion is already there because you have to plug in this all these estimators. So just as a completeness, oh boy. So this is there is a typo. So mu k would be simple like this. So this is a typo, and don't look at this formula. I know that you can compute this part. Okay. And pi k, if you do not know, if you don't like to put half, this is the sample proportion. The nk is the number of people from this group who has that type of symptom divided by total number of persons. So you can calculate that pi k as a prior. And then this is your, after plugging in these things, this is the whole thing is there. And why it is called linear discriminant function? Already it is said, if you look at this function, it is linear in the x. X is your feature vector, like your linear model. But linear model is not because of the linear of the x, linear model because of the linear in the coefficients. But the classifier here is linear because of the linear with respect to the feature vector. That's why it is linear, okay? It is not really by coefficient, it is linear, rather it is quadratic. So the example what I was trying to show you, you got this idea of, so I estimated all these things, and then this is the picture for the large number of new values when I am classified. This is the error, and the calculation showed the error is about 10.6% for one group. That means I misclassified class 2 observation as class observations for the 10.6%, and class 1 observation to the class 2 observation about 11.1%, which is just about 5% more from the nominal error rate. Because you cannot beat this part if there is, you have seen this 5% where it is, you cannot beat that part because there is obviously some commonality. So it is about, so it, in this case what we are trying to say that generally it works well. Again, you have to think about that the normality, all these assumptions has to be valid, otherwise it may not be that good. For example, if you have a big tail area, this type of classifier may not work well. Okay, but nevertheless it is very stable, works well, all these things are there. Okay, so very simple idea. We now know logistic, we now know LDA, all right, or LDA with p equal to 1. Now how about p? Usually in sense you never will have the p equal to 1, you will have p bigger than 1, like 2, 3, 4, 5. then your assumption would go Gaussian with vector mean mu and sigma. It is just a picture, probably all you know if you what is the density would look like. This is kind of the typical picture for bivariate normal density. This one is essentially when there is no correlation between x1 and x2. That's the picture you will see. It's kind of a bell-shaped because one normal distribution is like this and then you plot like that. But this one means when you will have some interaction between the features, like features are kind of correlated, then you will look like the surface would look like this. So what is this thing again you are looking? It is surface for this feature vector. Okay. So the more interaction will have these features, you will see all typical types of, like it's a hat, then here would be bent, this, that, all sorts of things you might see in the picture. Right? So then we repeat exactly the same exercise. If the observations in the kth class coming from multivariate normal, then plugging the density into 5, the Bayes classifier will take this form. You have to do some algebra, then you will get exactly this form. And what is this sigma? Sigma is the common covariance matrix from each classes, and mu k's are the different means. Again, as you can see that clearly we are trying to separate out based on the mean, and that's why you have to assume different mean, because once sigma is still kind of the same, but if you do the standardization of the data, usually it will be make much more sense, because two groups of data you have, if you do the standardization, then they might have the similar type of variance. So that's what it would be, but it is not necessarily true all the time. So then you assign for the new feature vector once comes in, you calculate this delta and assign to the group for which this is big.
Before this,
yes.
Do we need to transform that with the x1 and x2?
Do the
Both the variables.
Transform in what sense?
In the sense that the variation in one and the variation.
So if 2 could be too high, then it may not be really applicable. So if you, yes.
For example, there is a difference of 10 to 20, and there we have 210 to 250. So
no, here is that is, so by number may not mean that big variances. Say for example, one feature is ranging from 10 to 20. Another feature is ranging from say 200 to 210. So they would be just difference by mean, but the variance within these two groups still could be the same. But the variance may not be the same. Say one feature is varying 10 to 20, another feature is varying say 200 to 400. Then the variance is not clearly not the same. So that's those type of things you have to think about. So as a result, what does it mean? That means we are assuming that sigma is same for group wise, but that may not be true. Okay? So again, some of the data visualization would help you. And sometimes I know, at least in practice, when you go to the practice, number of adaptation you have to make. Sometimes you make some transformation of the x variables, like your feature variable, so that it can look like Gaussian, because in general it won't be Gaussian. You make some changes, because in terms of the classification, doesn't matter whether I am using the transformed variable or original variables, because there is no interpretations I need. I just need to classify. So I make the transformation of all these feature vectors such that it can look like Gaussian. Once it look like Gaussian, then this one would work better. But if the feature, when you are putting as an input, if that distribution is not Gaussian input variables, then this may not work that well, because you can see that it is based on this Gaussian assumption, essentially. So let's take a case k equals to 2. If you take the k equals to 2, then we can just the two class, either 1 or 2, you can say 0 or 1, that's what we did. But in just for continuity of our notation 1 to k, 2 class 1 or 2, either class 1 or class 2, the Bayes classifier will look like this. Again, you have to do a little bit of algebra. This is an indicator function of this whole thing plus 1. The parameters again are unknown, as the way we have seen in p equals to 1. You have to estimate the parameters and plugged in, and then you get the LDA. Okay? So again, how to estimate the parameters? For mu1 estimate, you use the test set from the class 1, take the mean, that would be your mu1. From the class 2, same way. This one, you combine the data together and then estimate the sigma. But note that you will have to estimate at least 2 variance component and 1 of the covariance components. So 3 component you have to estimate for this sigma. All right. So you can estimate all these things plugged in, and then it can go through. So same way it will work. Okay. So what we said, this case is when I have my feature vector which is more than 1 dimension, right? Say 2 dimension, 3 dimension, 4 dimension. But the third problem, if we do the classify, then like so your feature vector has the gene expression which has 20,000. Usually you classify based on, in a hospital you will have several 1,000 patients if you are lucky, record of this 1,000 patients or even 200 patients, but this could be 1,000 dimension, right? So you cannot really apply this thing. So what to do, that's the, as the new data coming in, that's the thing again. If I get time, I'll come back, otherwise, but you can see that this does not work, right? That's what I just wanted to make sure that you understand. But this is the part of the research. This is the current research essentially, huge literature going on, but not in the field. But until this part is well established and number of softwares in R you can call, and type of data set what I can understand you guys are working should be fine. You should have no problem.
Sigma if it is identity, then may work.
If you take, yes,
That is not the real case.
That's not the real thing. That is the thing. It is not the real thing. But what it gives, so you read a good point. So what it raises actually in terms of the research when you are doing, you are putting a lot of interest, as I said that last day, although we are doing the variable selection, actually we have to do the sigma selection as well. So some of this lasso technique I can apply to select this thing as well, because again, what does it mean general sigma means? All the feature vectors are correlated. But last day we said X are nothing but your covariates, right? And what we said, that most of them are useless. So how about I use that idea, so get rid of all this useless guy, then this dimension from 20,000 I can make it to 200. Then there is a possibility to run, right? So you have to basically apply this. So I told you several times how powerful those ideas are. You have to apply somewhere here, and then you can manage this thing. So you have to garbage out, although it's ideally it should be 20,000 dimension, but all the genes are not required to determine where it would be. Whole things require lots more derivations, but idea goes same way. So you reduce this dimension from 20,000 to 200, 200 to 20, and then regular things can go through. So that's what it is very important to understand this. Eventually you will be using the R, because all other things you will be using lasso type of technique to reduce the whole thing. Final stage you will run the R to get this answer done. Get the idea? So I'm glad that you guys getting the idea that if what the problem would be with the big data. Good. So I'll come back to this high dimension. Some of the things I know right now because that is my research interest at this point. I'll show you particularly for the brain data how I'm handling this part. But otherwise, at least if you know this thing, that should be good enough. Okay. So we talked about logistic regression, we talked about Bayes classifier, and then related to LDA. Now you remember that we have started with one of the non-parametric procedures, K nearest neighborhood. Since I have been saying that regression classification there is no difference, since I have started with K nearest neighbor regression, I have to end up with K nearest neighbor classification. So you can use the same technique to do the classification as well. Everybody remember how to do this regression, right? Y equal to or expected value y equal to fx, or f would be you have to take a neighbor of the new observation x0, and then you take the average of y values who belongs to that neighbor, right? And that's the way you estimate the f hat locally. Same concept goes here. You have to first fix a integer k, like what is your neighbor size, k equal to 1, 2, 3, 4, all these things. Given a test observation x0, that means when a new feature comes in, you have that's the notation is x0. The k nearest neighbor classifies, first identify the k points in the training data set that are close to x0. That means you are creating a neighborhood from the training set. Okay? So once you have a new patient, basically I am looking how close under the training set, which patients are very close to the new patient. Then I look at those neighbors' characteristics in my training set. And then from there I'll calculate this conditional probability that x equal to x0, what's the probability that y equal to 0? What does it mean? That means once the new patient comes in, I'll calculate what's the probability that it belongs to class 1, it class to 2, class 2. That, how does it happen? Basically I'll see that how many patients from group 1 close to the new one, how many patients in group 2 close to the new one, how many patients in group 3 close to the new patient, and that's the way this probability will be calculated. This is nothing but that's the way you calculate the probability. And k nearest neighbor decide the classification with the largest probability. So very simple, and you can see that there is no assumptions needed other than what should be the k. That's a big factor. And we have seen, I told you that first day, like mean square error, how it varies with respect to the k also. So those problems, but otherwise it's the even much simplest concept. And that's why very popular in computer science actually. They use left and right k nearest neighborhood for this big data classification. That's what I wanted to do it here. But I also, yes?
Using random variable to select the closest place,
No, let me show you how the way, one of the way, I think I have this, okay, here is this thing. So suppose this is your training data set. Some of these round dots of all the round circles, all these circles are your training data point. And these two different colors are from two different groups. It define the two different groups, okay? Disease group, non-disease group. Then a new guy came in. So this is the new guy. Okay? Then what you are doing, once the new guy is there, centering the new guy, you are circling a neighbor. What is the size of the neighbor? Essentially that's the k. K equal to 1, k equal to 2, k equal to 3, that's what you are trying to do. So you calculate this neighbor. Okay? Then within the neighbor, then you are seeing how many are from class 1 and how many is from class 2. Then simple probability concept, if I calculate the probability, this guy is much closer to this. There are two of them are closer from the group of these blue circles, but this is closer only one guy from this other group. So it is more likelihood then, or more likely that the new guy would be close to the characteristics of the blue, because its neighbors are like this. So as I said, k equal to 3, that's the way it is. And then based on this, if this is the picture, you decide essentially new guy belongs to this blue group. Then next guy comes in, wherever the value in this, because you use that coordinate system, you use there, then draw the neighborhood and see the same picture. That's the basic geometry of this idea. It's very simple idea, right? If you can do all these things, then like our Bayes, the Bayes classifier or the LDA classifier, we had a straight the boundary line, but here the boundary line is not straight. Like it's kind of, this is the class where the group are divided. This is the blue group, and this is the group, the yellow group. So this is the boundary line, which is very arbitrary. All these things. So if your neighborhood selection is perfect, you can have the best performance from the nearest neighborhood. Because you can see that it can very much separate out, only say one point is in the boundary, otherwise all are separated out. So problem number 1, we don't know it is too difficult. Suppose I know, somehow suppose one day I become the god, it's like getting a lottery ticket. One day I had this luck, I did this thing, but then what the problem or the statistical implication would be, still I cannot say that it is good or I am happy, because you can look at this boundary, how the way it is. As a result, the whole system has lot more variability. But LDA has the straight boundary. So LDA is very, very stable. This one has much more uncertain. So what does it mean? That means for this given problem, I got a lottery ticket, that's why my neighborhood defined was so good, I get a perfect answer. But next day when I am going to do these things, I did not have the lottery ticket, and I might have a much bigger mistakes, because so high variability. Okay? So that's why it is much less reliable, but much more simpler. It's very easy to compute, very fast, very easy to understand. You don't need to really understand the statistics. Only the last point what I said, why statisticians do not like it, because it has a higher uncertainty. But most common people do not care about the uncertainty. Let me do whatever this time I'm getting. I don't care what I'll get next time, right? But it cannot give you the guarantee that it will do so much accuracy each time. So, yes.
In this classification, so what if my training sample is huge? So in order to find out the nearest neighbors, first I need to compute all the distances between the points, right, from the new observation. So I mean,
that is one algorithm, but we don't. There is no real optimal way of doing this thing. That is the thing, problem.
That's what my question is. I mean, is this? How fast is this?
Here is also it depend. Who said that you have to do calculation from all points? That is the thing. If you do from all points, it may not be that fast with a huge number of things, right? But idea is that you really don't need to. Why don't you just look at predefined way? Because from the whole data cloud, you might have certain idea like 2 sigma distances. So basically what, being a statistician, I would expect most of the data point would be 2 sigma thing, right? So you have to apply all statistical, but what the machine learners never do that thing. So that's the way. So from the whole data, I can have some idea. It's not the exact sigma I'll get, but I'll have some idea. Then I'll just probably go with 1 sigma, say, even not even 2 sigma, depending on the data density. Like if it is a very sparse data, probably I might go 2 sigma. But if it is a very dense data, then I might go with 1 sigma. Because within 1 sigma still, under Gaussian type of things, you'll get 33% of the data point over there. And it might work well. Although it doesn't require any things like Gaussian assumptions or anything. But suppose if it's kind of approximately Gaussian, then still I will capture about 33% of this thing. My data will be much faster. But I cannot give you any theoretical guarantee that this would be better in terms of optimality or in terms of bias reduction. I cannot say this thing. Make sense? So that's why it is much more ad hoc. Still it is ad hoc. But if you like to do for all possible points, it may not be that faster. But in general way, computer scientists always think, oh, I have a big computer, I can do that. But that's not the way it is actually. Okay? So simple non-parametric approach, and one of the very primitive approach, by the way, often works very well. This is the point. Often works very well. That doesn't mean that, and there is no theoretical way I can tell you that this would work, this situation better, or this much percentage it will be better. Then I cannot say anything. I don't have the theory. And most importantly, as we have seen for this nearest neighbor regression, k could be the very big culprit. It can kill you the everything, but it can give you the best result. Like as I said, getting a lottery type of things, it might happen. So here is the fun thing to look at. Again, from a simulated data, how the error rate, classification error rate changes as the way you are changing the k. 1 over k higher means k is smaller, and 1 over k higher means k is bigger. Okay. So as you can see, so this is kind of the Bayes classifier, this solid line. That's kind of a standardization without doing anything. Under Gaussianity, I can prove some optimality of the Bayes classifier. Okay, that's why Bayes is the kind of the standardization. So under the training errors, for the training set, if you do, because you are using the training data, then your error rate might go down and down, even for k is smaller and smaller. But for testing string, it may not happen. So what you see in the training data, that may be completely different in the testing set, which you are interested in. So although as I said that I don't have the theory to say, to back up much things, this kinds of gives you some idea how it might work compared to the Bayes one. Okay? And there is no way I can say, so when it is kind of the better after this point, that means k would be this, no way I can say this part in general. All right? So you learned actually three most powerful classifiers, logistic regression but logistic classifier. Let's talk this thing, LDA and k nearest neighbor. Now there are multiple variations, so you can learn by yourself, okay, whatever the variations are. So as I said, in modern days, life is little more difficult. P could be bigger than n. What does it mean? That means number of features is much bigger than the sample size. Then obviously LDA is inapplicable, because anybody can think that this would be singular. By the way, still LDA is the most popular thing, not really nearest neighbor, because of this complicacy. In LDA, there was no parameters you do not know, because you can estimate using the maximum likelihood, using the method of moments under the Gaussian assumptions. So everything is, you can have a data driven as long as Gaussian density valid. So that's why there is no tuning parameter as such. But here there is a tuning parameter k, and which could be killer. That's why it is not that much popular. So for this one, this is the research in after 2010, I would say that's the begin. Number of development happen. Let me touch base couple of them, and then so one is the simplest way. So what would be the things? You can see the formula again. Okay. So this would be the formula, and what we are talking about, that this guy is a huge dimensional thing which is bigger than n, the dimension. So first idea, kind of first or second, I don't remember when it is. It came from Evan Bickel. Some of the stat guys know who is Bickel. You guys read the Bickel Duxham books, right? That's the same Bickel. So what is his idea is, general estimate of the sigma would be from the sample covariance matrix, and which is singular because of the p is bigger than n. By the way, even p is not bigger than n, suppose p equal to 4 or 5, it's a very unstable estimate. You should not use that. But in LDA, this is a big factor because this is a standardization guy. So what he said, you take the diagonal version. Just take the diagonal. So you calculate this sample covariance matrix, which is singular, because sample covariance matrix, you as many data points you have, you just take this x minus x transpose, that's the sample covariance matrix, take the over sum, but don't do the inversion. You just collect the diagonal without calculating the inversion, so which is easy computationally, say d hat, and then plug that d hat into the LDA. So essentially it's a diagonalization. You are treating that case kind of independence, because diagonal means essentially it's not identity matrix, but you don't need to invert anything. It is 1 over this thing. It should be fine. So that's a very simple proposals. And then of course he tried to show that asymptotically it achieved that optimality. What does it mean, optimality? That in worst situation I should have the probability of making a mistake no more than 0.5, right? If it is more than 0.5, I should not take, because 0.5 anybody can do it. Flip a coin, the guy is here, I'll decide whether he is this group or that group. So 0.5 is the optimal probability of making a misclassification. So what is this procedure, you can show through some mathematics that it can achieve that lowest error rate could be the flipping a coin. Otherwise it could be better. So, but note that you might start criticizing everything, you do it so that you can write a paper. But that was the first idea came. Okay, and you have to do the mathematics to show how the way error is there. Okay. Second one, instead of second one, I'll just mention few of the developments. By the way, most of the papers are in Annals of Statistics. In after 2005, 2006, those type of things. So the fair idea, which is called the feature annihilate independence rule. So idea is, note that in LDA, where we are trying to look at the difference in the mean and some kind of standardized mean, because mu minus mu transpose sigma inverse. So look back the T statistics, this is nothing but the standardized mean. So what is the idea is that first let's look at where the differences, component wise differences in the mean. So you have a feature vector from group 1, you have feature vector from group 2. But we already thought that everything is not different. Some of them are different, some of them are same. In fact, most of them are same, some of them would be different. Like effective 20 genes would be different, all others are same because all 0. So try to identify where they are different. So you do simple pairwise t-test component wise and try to see where the difference is. Okay. So basically how many tests you will be doing? If the 20,000 is the dimension or 20,000 is the feature vectors, then 20,000 you do the test. And then you collect those components for where this test gives you significant differences. Then you select those variables for which, as I said, among the first essence is the largest. So you basically make some threshold. Just don't do exactly p-value type of thing. You make a threshold because when you reject this hypothesis if it is bigger than some quantity, right? And in simple statistics, you try to find out that simple bigger than some quantity is the t-value. But instead of using the t-value, you should be much more conservative. That means you fix up some threshold such that at least 200 variable or 200 difference would be there that you can control by choice. So in other words, you don't do a perfect statistics job, rather than do some sensible work over there. And then collect sum of the coefficient. If I take the sum of the coefficient, then use those component into your sigma matrix. So your sigma matrix dimension would become about 200 or so from the 20,000s, and then use this whole thing. So it's not really total diagonalize, but it would look like this one. Note that this thing is not the diagonal matrix exactly, it's kind of a banded diagonal. And what is the band dimension? As many components has been collected from this t-test. So everywhere some ad hocness is there, but this one would be again, now once it is that banded diagonal and this S dimension has to be, you cannot select the number of component more than the sample size again. The same phenomena is coming. You can see that whatever I talked about in the lasso, exactly the same ideas. So that's why lasso is so powerful idea. You have to apply. So these things are all coming from that thought of dimension reduction. So once you have this thing, then you apply this part, and the claim is that the fair can select all the useful variables with probability in this rate, log p equal to lower order of n. That means if your p even is exponentially increasing than the sample size, still it can do pretty good. Okay, that's the mathematics. You don't need to prove, but what he is saying that essentially p could be exponentially larger than the sample size, which gives you a lot more flexibility. Okay, and then it works well. So this is 2008 annals. But again, don't expect me to provide you these codes, because even all these are recent research and there is no available code is there. If you have to get the code, you can get from these authors itself, but even commercially or reproducing other research, I may not use it, because still it is not very highly verified. It's not one of the LDA, okay, or it's not even nearest neighborhood one. So what is the crux of the matter? Crux of the matter is somehow you have to reduce the dimension, and it will work only under the assumption that, again, if the differences, high differences belongs to a low dimensional manifold, from a high dimensional manifold to low dimensional manifold, then only things can work, and then we can do the mathematics as well. If this thing does not exist, that means if I cannot prove that the number of significant differences is less than n, I cannot do anything, any of this proof, and it cannot work. Even by theory it cannot work. So same idea. Now naturally, as I said, that this is so powerful idea, you can apply, you can think about number of different things. Another one, what is called the LPD, linear programming discriminant. So if you rewrite that LDA, what the expression is, you may see that essentially mu2 minus mu1, that is the difference you like to capture, as I have been keep saying, this is the guy who do the discrimination. You can write in this way. Okay, you need some manipulation, you can write in this way. And then what is your beta dimension is? Note that sigma is a very high dimension, like 20,000, so beta is a 20,000 dimension, which we cannot do this thing. We need to have a dimension reduction. Kind of similar idea of the lasso type of things, which I spent whole morning. You are applying, but with infinite norm. That's a proposal. That doesn't mean that other norm would work. What is this infinity norm? Everybody knows? Yes. So maximum of these differences would be less than lambda. So if the maximum is less than lambda, then all of them will be less than lambda. But this is another proposal. Once you have this thing, then you propose this classifier. See that you are estimating this thing with these conditions. There is no inversion needed. Then your classifier becomes here. You can see that you estimate this LPD plugged in here. You classify your things. It's done. So computationally, if you can handle this part, then next part is use just the simple R code. But this part you have to develop. And so you can already now you can see some similarities. If you learn that algorithm for the lasso, you can develop some things here. Okay, so that's what I've been keep saying, that when you go back, you try to learn a little bit more on the lasso. All right. In this way, number of I think I'll stop it here. Like road, regularized, optimal, affine discriminations. All these things, procedures, is that you have to assume some of the sparsity is there. All right? Make sense? So, but this is under the current thing. So if you are thinking about solving big problem, these are the big problems you have to work it on. And related theory also is very useful. It's fun to do, but it's beyond whatever we just. It's not just textbook type extension. Okay, so I think I can spend another 5 minutes, since we have been talking about real data as well. At least I have something to talk about from the brain image. As I said, my most interest is right now in brain image. So let me because I don't think that in the afternoon we'll have the time to go too much of this. This is any question? Everything makes sense? Right? Interesting. So stat people also getting some flavor. You guys can do it easily, right? No? How about the theory part? Or propose something new, which is sensible. Propose something new. So here is my good advice from stat people. We have to also always think about that. Stop saying that the computation part or the theory part is also not obvious. It is not at all obvious. If you have to have a sensible solution, you can have a theory which may not be sensible solution at all. As I said, like we have learned multivariate regression, but give her that multivariate regression MANOVA type of things, she cannot apply at all, because big covariance matrix involved even with 5-dimensional y vector. So it is useless. So that's why the PLS people, and PLS came from the other people, not from us. And now you can do the theory for PLS is difficult. All right. So as I said that this is, I wanted to talk more on the spatial, but forget it. Here is some part from one of the current students' thesis actually. She is very good, I think. So here is the starting point. We started with some of the MRI data, fMRI data, right? And this is again some of the slice of our brain. And I told you that how the way data would look like, basically each voxel level. So basically you chalk to your brain this, and then this. So 3 way. So it's a cubicle, and you have a million of cubicles are there. And what is this? This is a kind of a normal brain, and this is the brain, the people who has certain Alzheimer's. Can you see some differences? Already it is some of the arrows are there. You can see some differences. These 3 regions, whole brain you cannot see the differences, but there is some differences. But truly, in a data way, you will see millions of data points here. But the whole image, from the image first you can see some, this is the image essentially. This is not the real data. From this image you have to process the data. So clinically, I have 1,000 patients which I know from the Alzheimer's side and from the non-Alzheimer's side, the normal patient. Now the new guy came in, like I have said Alzheimer look like, because I cannot remember many things often. So probably that's why I also went and did my brain scan. But including my students also did this brain scan. Actually, my interest was to see how the scanner works and how the way they take the data. But idea is, when the new patient comes in, you have to say whether it belongs to here or it belongs to here. How do you do that? It's a classification problem, but how do you do that? You will have a training set. So as I said, the training set more probably you have 1,000 patients already collected. But by the way, this is a very harder problem, because the reason is biologically, Alzheimer is a very slow disease process. It's not like the curve we used to, oh, this is the curve, so you can find a change point, all sorts of things. It's so slow that capture the differences is too difficult, and data might be available only last 10 years, because before 10 years before even we didn't have that technology, because this whole technology is coming up soon. And still it is fairly expensive to collect all the data, process all the data is very, very expensive. So question is, how do you do that? Now look at little bit more carefully. if I look at this part, so again, you should not think about that this is a one piece of data, but this is like point. This is kind of the dense area, means like looks like that some of the neurons here are kind of similar. These neurons are kind of similar. These neurons are kind of similar. That's the way it's kind of the picture. So typically in the literature we call it's kind of a special pattern, because nearby neurons are look alike, like more like two of you would be more alike, so you'll have some kind of dependence than you and my or myself or him or myself. So we can think about independent, but you cannot be independent. So what does it mean? That they are not necessarily, all the points are not necessarily independent. Not only that, LDA, we assume that whole thing is totally Gaussian, that means same covariance matrix, but actually the covariance matrix changes depending on this region versus this region versus this region, so covariance matrix changes. So we cannot have the same covariance matrix. Everybody agree with me? Then how to do that? So what idea is that we like to develop again LDA type of things, because LDA, I also love LDA so far. Again, I don't think that there is better alternative than LDA in terms of stability, in terms of understanding theory, etc. It's better. So as the way we started, so this is your feature vector. This YKI means there are K classes. Here it would be two groups, and I means individual in the ith class. So like 500 Alzheimer patients, 500 non-Alzheimer patients, and this is the feature, which is the P dimension could be millions or something. And then this is the covariance matrix. So you already know that LDA classify, this would be the formula for the LDA. Okay? And we talked about, this is the formula for sigma hat, but for P bigger than n, this does not work. So for this, particularly this type of problem, so what is the, since we have seen the covariance is actually, the covariance structure depends on the location where you are talking, where you are looking. So the feature vector, still it is a Gaussian, but given a location, it has a mean that location, but the covariance between two locations S and S prime varying with certain function gamma. This is kind of the covariance function. So where it locates, S and S prime is the location, it will define this covariance. So what does it mean? That means by using this appropriate, choosing this function, I can make, if S and S prime is here, then I will have one type of covariance, and if S is here, S prime is here, I can make it 0 or different, right? So that's the flexibility I get by defining this covariance function. So if I have this thing, and general way, simple starting is, it would depend on the distance between these two, and you can define the distance even in three-dimensional way, although it is nothing is obvious, but you can do it. So then what would happen if I have this structure? Eventually what I am trying to say, that this is your feature vector, this is the feature vector mean, and then the covariance matrix, which is the trouble, that is will be known if I just know the parameter theta. And what is the parameter theta? That is define the covariance function, how it is changing the covariance depending on the distance. And distance is the data, so it is known. Only the parameter theta I have to estimate. All right. Now there are different types of choice you can take. So all different types of choices are here. For example, if you think that it is exponentially decaying, then this could be one of the choice for the covariance function. Then if you think that equal covariance, then this is the equal covariance, doesn't matter what distance it is, just 2 points are correlated, then this is generally useless, but in some cases it could be. This is also, in my opinion, useless, but this is at least in this aspect, but this is used in econometrics and all other literature, so you can use all this. So you can give the choice. What at this point we are trying to develop as a general methodology, and then we'll see case by case basis. Then there is a polynomial structure which might even make sense. the distance at is increases since rho is between 0 to 1. So suddenly after certain value, these values would be essentially close to 0, or you can just make it 0. Okay. So then if we do the LDA, then we have to estimate the parameters as usual. And since I have the Gaussian likelihood, this is a Gaussian likelihood, then you can write in this way. Then you maximize, note that you maximize with respect to mu1, mu2, and with respect to theta. If it is low dimensional, at least you can do this thing with a maximum likelihood estimate. And sigma, you really are not estimating with a very high dimensional way, you're just estimating only 1 or 2 parameter theta. As a result, it is much more meaningful if you can capture this way. But also note that we don't need to do the diagonalization, nothing. So this should be the thing. And then you plugged in there. So if I do that thing, how does it work? So basically this is the first stage we wanted to see. As already you have seen that all this other existing thing is some kind of diagonalization, but here I'm not trying to do the diagonalization. How it works, if I known the true covariance matrix, true, then the classification would have been like this. And what is the R defined? R defined, the higher the R is, that means highly correlated are. So it is essentially defining correlation changes depending on their locations. If I known the everything truth, then this would be my error rate with only 36 dimension of the feature vector and n equal to 60. So this case is p is still less than 60. And if I estimate this thing by maximum likelihood estimate, then this would be the error rate, which is very close. That means maximum likelihood work here well, and this makes sense because you have 60 data point and you are estimating only one parameter for the theta, so it should be much more stable. And mean vectors are always you can estimate because mu1 from this data you are just taking the average, so this is very stable estimate. P equal to 100, which is bigger than 60, p equal to 400, which is bigger than n. Now look at that when you do the MLE, truth means you are not doing any estimate, you as if you know everything. Compared to this part, you can see that the performance is not as good as it was here. So it is deteriorating in this situation, and which makes sense. Even you increase to further like 60 and then 900, 1225, you can see that further it will deteriorate. And what we like to reach, let me show you if I have that data part. So here is the eventual data at this point what we have. So left whole MRI scan, this is the MRI scan, it has about 10 million point, but we know that we cannot handle 10 million. But white matters has, so white matters you can actually erase. So even in the image you can see the white matter, then there is a software, you can erase this thing. That has about 300,000. And right one has about 4,568. Now some of the neuroscientists which we work with, that they said essentially you should not look at this point. They like to know only this part. And you have seen in the first picture, there is one pocket which is changing much. There are some other pockets also changing. That means change does not happen whole part of your brain, only some part of your brain. So this is the corner part. So this is happening about in this many. So this contains this many neurons, about in the 4,000 range neurons. So that means I have to handle this covariance matrix about in this range at this point. So that's what the simulation number was there. Okay. So long story short, how the way we are trying to do which portion I should show you. I don't like basically at this point you don't need to look at the theory, but idea is what we think. So this is the difference vector, which is at 20,000 dimension, the group 1 minus group 2, Alzheimer versus non-Alzheimer. But what we think that differences are only in S. P minus S, there is no difference. In fact, all of them would be 0. So I don't need to assume that the mean values are 0, but the differences are 0. So that should be good enough, because in a discriminant function I have to estimate the difference, not the individual one. But typical LDO estimate each individual mean values. But here I am not trying to estimate the individual mean value. We are reducing the parameter right there, at least half of that. And the assumption is that S is less than P. Not only that, S is actually less than the sample size, like number of patients I have the data, this is like there. So then you can write down all these things in this way, and then do some little bit more reparameterization, like define tau 1, tau 2. These are kind of your prior probability. Remember that these are prior probability. If I do, but this is known factor because this is from the data. If I do these things, eventually you can write down the whole likelihood like this. And keep doing some algebra. After doing this way, then eventually you can define for this type of case, the MLE would be like this. Okay? Now, there are two ways. Forget about this part. So think about this where is this? I did not put that slide that where I put the penalized one. So delta, oh, here you go. This was important to see. So this is the portion from this likelihood. Then remember that what this notation is, this would be something, P is the dimension, N is fine, this factor, this P lambda is the penalized one. And remember that lasso. So we are putting lasso type of penalty on the differences of the mean, not really individual mean. Because what is the assumption? The differences of the mean only for some of the neurons are there, most of the neurons are 0, differences are 0. So that penalty goes on the differences. So by this way you are actually reducing the parameters heavily. So what do you have? In the theta you have only 1 or 2 parameters, and here by penalization you are expecting only say 200 or 400 neurons should be difference, all others should be 0. So as a result, ideally with the same idea of lasso, it should work it out. And in fact, that's the thing, the proposals. And then what so far she did, of course there are many more. So tried to show some consistency result, like if you estimate these guys eventually, so this would be estimated with this much accuracy. The theta, which is the parameter in the that is also has the consistency with square root of 1 over NP. Note that it is much more explicit because NP P equal to high, then it is much better approximation. So generally in general asymptotics we don't look at the P because we assume that P is fixed. But in this case your number of features can depend on sample size as well. So that's why we have to be much more explicit on both the things. And then this type of asymptotics you have seen, but what is the most important thing we are saying, that with probability 1 you can have a root n consistent estimation of this delta. What is the delta? Delta is the differences of these neurons, and where the differences, that differences will be differences, and delta P minus S, this P minus S component, they would be exactly equal to 0 because there is no difference and we are not interested in. So this is kind of the parameter consistency you can, so in other words what I am trying to say, that you can have theoretical foundations for that, and then some of this, like where the error rate might go, it's kind of trying to say that probability that 2 would be classified as 1, probability goes to 0, 1 would be classified to the 2, probability goes to 0, so that it will really have the properties what you look for, like asymptotically error would be much lower. Of course in reality it could be. So these are some of the mathematics still I think I have to check, but what I'm saying that it might work. And if we apply to this type of data set, then in terms of the performance, still not that very, you don't need to look at all these different variables because these are different biological measurements. Just look at one of these things, maybe this one. You know that in this 2 by 2, this is called the confusion matrix, right? Sensitivity, specificity, accuracy, and then yes. So accuracy is kind of pretty high. Specificity is also very high with this way. And what we are handling about, you have seen 4,000 voxel. We are not still dealing the whole brain yet. But somehow sensitivity is still pretty low. So, but the methodology is kind of working or underdeveloped. So these are the things are not still in the literature, but these are the big problem. Since this course we said that we'll introduce you some of the big biomedical data problem. These are the big biomedical data problem. These are the technique that you need to develop. So this would be the case. But you have seen that you have to understand the basic part also very well to develop anything new. But hopefully down the line we can provide you some of the softwares, etc. But I need to understand the problem much more than I can provide you any solution. Unless I understand the problem, no solution would be a good solution. Okay? And this took me more than 2 years working with all the doctors and etc. to even, I don't think that I claim still I understand anything. Okay? But it's too difficult. It's too difficult, but it's fun to spend some time. But any kind of, so this is the brain problem because I'm spending more time with the brain. But I gave you some other example where you develop the computer models to model this your organ, like how your heart will beat. Without checking you, I can actually model the whole thing. That computer will take, of course, 30 days to run at this stage. So what we have to work it, good computational model. Once the patient comes in, can I tell you how your heart look like? And then if I take the image, can I have a better prediction how your heart look like? Because some cases you cannot take the image immediately, even the patient comes in. You have to wait a couple of days to do the scan, etc. By the time the patient might die. So how about if I try to simulate your organ? But these all are kind of big data biomedical engineering problems, and I don't think that computationally we are there yet, or even computer scientists are there yet. So anyway, what else? I think this was pretty good. But you got the good connection with logistic regressions and then k nearest neighbor things. All right? Okay, so let's take a break. It's 12:15. So I think then we should come back 2:15. Should be fine.